Okay, sorry, a little burp there in the presentation. Had to correct a typo. So we left off with r in the domain of the g function. So we get r equals square root of x squared minus 3x. Squaring both sides, r squared equals that square root squared, inverse functions, and it leaves us with r squared equals x squared minus 3x, which we can rewrite as an x squared minus 3x minus r squared equals 0, and we can solve for an x using the quadratic equation. So we get x equals negative b, okay, b is negative 3, plus or minus the square root of b squared, negative 3 squared, minus 4a, coefficient of x squared is 1, c, constant term, is negative r squared, that is, let's see, all over 2a, a is 1, 3 plus or minus, oh, look at that, you need the plus or minus on there, eh? That square root symbol would only give you the positive square root in this case. So we get 9 plus 4r squared under that radical. So we get 3 plus or minus 9 plus 4r squared over 2. Hey, 9 plus 4r squared, that's greater than or equal to 0. Actually, it's greater than or equal to 9. We've taken 9 and added something positive to it. So, indeed, such an x does exist. Actually, probably two such x's exist. We don't have square roots and negatives here, so these are legitimate solutions to this system of equations. Such an x exists, and so r is in the range of g. And we could take, say, x equals 3 plus the square root of blah, 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 all over 2. And that would give an x value in the domain, which would yield the r value. In other words, these r's we chose up top, greater than or equal to 0, they're all in the range of g. And the range of g is the interval 0 to infinity, including the 0. We could plug in what, x equals 0 and get out the 0. So you do get the 0 out as well. By the way, if we'll look at what the quadratic equation has given us, we get one x value in the interval negative infinity to 0, and we get another x value, it's down there at the bottom, in the interval from 3 to infinity. We had the domain consisting of two disjoint intervals, and in fact, this is a function that you want any particular value out. There's two input values that'll give you that value out for this particular function. This is what they are specifically. You want to get an r out, plug either of these two things in, and you'll get that value r out of the function g. So, domain, not so hard. Range, a little bit more complicated of solving this particular equation. We could do this because we had the quadratic equation at our disposal. Had that function g been more involved, if it had involved an x cubed term, for example, we probably couldn't have done this. So this one's special because we could use the quadratic equation on it. Back to the notes. Definition of a graph. If f is a function with domain D, its graph consists of the points in the Cartesian plane whose coordinates are the input dash output pairs of f. In set notation, the graph is all ordered pairs, x, f of x, x, y if you like, where x is in the domain of the function. So what we do, this you're familiar with, is we simply take input values x from the domain along the abscissa, along the x-axis, and then we find function values and go a corresponding distance up for positive output values or down for negative output values in the vertical direction as read by the y-axis, ordinate, I guess it's called. And you plot the corresponding points. And the collection of all such points forms usually a nice clean curve, and that's the graph of the function. So, you're familiar with certain kinds of functions, lines and parabolas probably, maybe some conic sections, which may or may not be functions, but you have some familiarity with graphing equations. In this class, piecewise defined functions are going to play somewhat of an important role in some of the examples we do, illustrating limits in particular. So instead of being given a single formula for a function, you're given several formulae which define the function in pieces. There may be several pieces, but we're still only dealing with one function. As an example, example 1.1.4, example 4 from section 1.1 is my numbering scheme. It says, consider the function f of x equals negative x if x is less than 0, x squared if x is between 0 and 1, including the endpoints, or 1 if x is greater than 1. This is a piecewise defined function. How many pieces are there? 1, 2, 3. How many functions are there? 1. Its name is f. It comes in a definition that involves 3 pieces, but there's only one function. It's defined in terms of pieces, piecewise defined function. So the function comes in 3 pieces, but yeah, there's only one function. You know how to graph lines and parabolas. So you ought to know how to graph y equals negative x. You ought to know how to graph y equals x squared, and you certainly know how to graph y equals 1. So we get a line with slope negative 1 up here. We get the parabola y equals x squared here. And in this part, this piece, we get the constant function y equals 1. So you can graph each of the parts in their entirety. Well, we'll just graph the line y equals negative x, but we'll just keep the part for x less than 0. We'll graph the parabola y equals x squared, but just keep the little piece of it between 0 and 1, including the endpoints. And then we'll graph the line y equals 1, but just keep it for x greater than 1. In so doing, we get this. The graph of y equals negative x in its entirety is a line with slope negative 1 that passes through the origin and continues on over here, but we only keep in the part for x less than 0. Parabola, the y equals x squared part would be a parabola. Have 0 as its vertex and continue on over on this side, but we're only keeping that parabola for x between 0 and 1. So that gives us this point, 0, 0, plug 0 in, you plug it into this piece. So we get the origin out, plug in 1, you plug that into this piece, and you get out 1. So it passes through the point 0, 0, 1, 1, and it's this little segment of the parabola here. And then we graph the line x equals 1, which is a horizontal line, y equals 1, except we just keep it for x greater than 1. And so that produces this function here. So if you can graph the pieces, then you can graph a piecewise defined function. Let's do a little example. Of graphing a function. Graph this function g of x. 1 minus x for x between 0 and 1, including the endpoints. The other piece is 2 minus x for x between 1 and 2, including the 2, but excluding the 1. Okay, both of these are lines of slope negative 1. Y equals 1 minus x is a line of slope negative 1, say m sub 1 for first line slope. And it contains the point, say, 0, 1. If I plug in x equals 0, I get out y equals 1. So it contains a point 0, 1. By the way, since x is 0, that's the y-intercept of that line. The other piece, y equals 2 minus x, is a line with slope, say m sub 2 equals negative 1, the coefficient of the x in both cases. And it contains, say, the point 2, 0. If I plug in x equals 2, we get out y equals 0. Oh, since we're getting out y equals 0 this time, that's the x-intercept. Y coordinate 0, we get out the x-intercept. X coordinate 0, we get out the y-intercept. So for variety, I've chosen an x-intercept in one case and a y-intercept in the other. Yeah, it is for variety. It's also by my constraints on what x values I use on which piece. So we'll just graph those lines. Let's graph a line with slope negative 1 that passes through the point 0, 1. Okay, here's the point 0, 1 right here. Line of slope negative 1. So run it over to here and stop because we only take that line for x between 0 and 1. x equals 0 to x equals 1. We'll take this line, including the endpoints, so we get the solid circles on the end. Then we switch over to the other line. Let's see, this had the point 2, 0. 2, 0 is right here. Also a line with slope -1, so we can extend it downward with a slope of -1, or upwards or backwards, slope of -1. And we keep this line only for x between 1 and 2, excluding the 1 and including the 2. They excluded the 1. What's up with that? It's supposed to be a function. It satisfies a vertical line test, doesn't it? If we colored in this point as well as this point, we'd violate the vertical line test. So that's why they've joined it very precisely like this, including the 1 in one place and not the other. How many functions do you see graphed here? 1. Its name is g. So this is the graph of y equals g. It comes in 2 pieces. It's a piecewise defined function. It's not a continuous function. You couldn't draw it without picking up your pencil. It's got a discontinuity at 1. Continuity is a topic of calculus, and we'll explore it using limits in chapter 2. Back to the notes. Another function we'll see, not a great deal of, but it'll pop up in calculus now and then. When we talk about one-sided limits, it'll pop up. In section 2.4 is the greatest integer function, and another one is the least integer function. They're indicated with, magnified a little bit more. The greatest integer function is indicated with these little brackets with little bitty bars at the bottom. It's the rounding down function. And the least integer function is a rounding up function, and it has these little bars on the top. So that's the notation for these functions. And what the rounding down function does, the greatest integer function, what it does, if I take a number, say between 1 and 2, it rounds it down. So if I plug in 1.5, we get out 1. Yeah, it loses that 1.5. It loses the half part and rounds it down to 1. I put in 1.9, it rounds it down to 1. I put in 1.9999, rounds it down to 1. I put in 2, rounds it down to 2. So it rounds it down to the next highest integer. When you put an integer in, of course, you get that integer back out. The book has drawn this little 45-degree line showing that this fixes the integers. So 2 is mapped to 2, 3 is mapped to 3, and so forth. I think that's their implication. It's not part of the graph. The blue thing is the graph. This is maybe called a step function because it looks like steps. It's not continuous, so we need some discontinuous functions to illustrate some of our calculus ideas. The rounding up function, it's got the same kind of shape, but it's a different function. Now, if I take a number, say between 1 and 2, like 1.5, it rounds it up to 2. I take 1.999, rounds it up to 2. I take 2, gives out 2. I take 1.001, just a little bit bigger than 1. Well, it's gonna round it up to 2, for example. So the difference in these two functions is this one on the right, the rounding up function, is the one on the left shifted up by 1, except along the integer values. So basically, the steps have been moved. Did I say it correctly? These steps have been moved. The best way to look at it is shifting it to the left. It's shifted to the left by 1, I should say. Except at the endpoints. We got some kind of oddball behavior at the endpoints. Both of these functions fix what happens on the integer values, and that's why they've got the 45-degree line there. But anyhow, it's a discontinuous function. They're both called step functions because they look like steps. And they'll be useful when we deal with some of our limit ideas in chapter 2. Definition of an increasing and decreasing function. This will be probably stated again in chapter 4. We'll use increasing and decreasingness to help us graph functions. Thing is, now you don't really have a nice way of determining when a function is increasing or decreasing unless you have the graph. But calculus will give us a way to find when functions are increasing and decreasing. So let f be a function defined on an interval I. Let x1 and x2 be any 2 points in that interval. if f of x2 is greater than f of x1, whenever x1 is less than x2, then f is said to be increasing on the interval. Okay, does this make sense? When we move to the right along the real number line from x1 to a larger x2, greater x2, the function value gets greater. So increasing input values yield bigger output values. Yeah, that's an increasing function. If we put bigger input values in and got out smaller, did I say it correctly? If we put bigger input values in, put x2 in, larger than x1, and got out lesser output values, then the function's decreasing. Of course, pictures look like, let me scan down, here's an increasing function. When I put in bigger x values, greater x values, I get out greater y values. It goes over and up. It's not a line, but it's still if I go over to find a point on the function, I have to go up. So there's an over and up to it. This is decreasing for negative inputs because when I go over, that is, I increase the input values, I have to go down. I get lesser output values for the left-hand part of it. It's increasing for the right-hand part. So, definition of increasing and decreasing, and it means the very intuitive idea about a function going uphill or downhill. Maybe one quick little warning on that. This function goes downhill and then it goes uphill, right? Downhill here, uphill here. Of course, I got to read it from left to right. If I view it from right to left, I get all those things backwards. But you view it as read from left to right because that's the ordering on the real number line. The lesser numbers are on the left and the greater numbers are on the right. This is an increasing function when read from left to right, and that's the way the number line's laid out. It's difficult to tell whether a function's increasing or decreasing unless you have a graph. Well, if they ask us anything about it at this stage, they'll give us a graph. But the story is, we won't get better graphing stuff. Turns out in section 4.3, we'll have a method related to calculus stuff, derivatives, to determine whether a function's increasing or decreasing. And we'll use that increasing, decreasing information to create a graph of a function. So one of the main applications of this calculus stuff is to learn things about graphs of functions and to become better at graphing functions. Not to belittle your graphing ability, but it's going to get a lot better in calculus. Right now, you can only graph a few special things. A function is said to be an even function if, when I take the input x and replace it with negative x, we get the same function. F of negative x and f of x are the same. It's said to be an odd function if f of negative x is the same as negative f of x. Here's a couple of examples, those things we were looking at a second ago, of an even function and an odd function. So an even function is one, when I plug in x or negative x, I get the same output. Here's an x value, and here's the corresponding negative x value. When I plug the x value in, I get out this y value. When I plug the negative x value in, I get out the same y value. That's an even function. In fact, we'll state on the next slide, an even function has a symmetry with respect to the y-axis. Possibly you've encountered this in pre-calculus. And this is the function y equals x squared. The reason they're called even functions is related to the fact that if I had y equals x squared, I get a function that will basically absorb the negative sign. The squaring absorbs the negative sign. If we had x to the 4th power, it would absorb the negative signs as well, or x to the 6th power. So those even exponents will produce this kind of behavior. That's the reason they're called even functions. Hey, guess what? If we graph x cubed, it's got this kind of symmetry. So what it says, if I plug in an x value, get out some corresponding y value, produces this point xy. If I'll go to negative x, plug that in, I'll get the negative of the y value out. So by changing the sign on the input, I get the same sign change on the output. If xy is a point on the curve, then negative x, negative y, or negative x, negative f of x is an output. So the output values differ by a negative sign when the input values differ by a negative sign. This is called symmetric with respect to the origin. If I go over and up and find a point on the curve, if I'll do the corresponding thing but go back and down, I'll find another point that lies along the curve. So when I draw a line between those corresponding points, it'll always pass through the origin. That's what they're getting at with their little arrow here. Another way, a little less politically correct, is to say, hey, even functions, they suck up negative signs. They just disappear. Odd functions, they spit out negative signs. You feed it a negative x value, it spits that negative sign out. And it results in these two kinds of symmetries. This happens when we have odd powers of x. This kind of behavior will happen when we have odd powers of x. Take a negative number and cube it, you get a negative number out. There's some behavior of spitting out a negative sign with odd powers, and that's why those are called odd functions. The symmetry these graphs have, as I mentioned, are called symmetry with respect to the y-axis for the even functions, because it's a mirror image of itself about the y-axis, and symmetry about the origin, or symmetry with respect to the origin when it has this kind of behavior. This one's a little more subtle. This one's a simple mirror image here. This one's more subtle, and that's why I've drawn the arrow as well. And possibly you talked about symmetries of functions in pre-calculus. They're easy to check for symmetries. Actually, let's do one. Okay, here's a function, h of t equals 2 times the absolute value of t plus 1. Is it even? Is it odd? Is it neither? Okay, I don't see any even exponents in here, but they got an absolute value on there. I'd expect that'll absorb negative signs, won't it? I bet you it's an even function. Let's go through and show it. Okay, to test for even or oddness, we'll replace t with negative t, x with negative x. They've given us t as the variable here, and see what happens. So we'll take h of negative t. So go to the function. Wherever I see a t, I'll replace it with a negative t. So we'll get 2 times negative t, absolute value of, plus 1. 2 times negative t, absolute value of, plus 1. Whenever I substitute into a function or an equation, I'll probably put the stuff I substituted in parentheses. And I'll use parentheses for a lot of stuff, but I'll try to consistently use them for that. So we've replaced in the definition of the function the dummy variable t with this input, negative t. I put it in parentheses so you can see what's substitution and what's just stuff left over from the definition of the function, like the 2 and the 1 and the absolute values. So we get 2 times the absolute value of t plus 1. If I go back and use my properties of absolute values, this is in, I think this is in Appendix A1 as well. The absolute value of the product is the product of absolute values. So treat this as negative 1 times t. And then we get the absolute value of negative 1 times the absolute value of t. Of course, the absolute value of negative 1 is positive 1. And oops, I'm missing a plus 1 right there. But we get then 2 times the absolute value of t plus 1. Oops, missing a plus 1 there. And that's what h of t is. So we take t, replace it with negative t, we get the original function back. That's what happens with an even function. Had it spit out a negative sign somewhere in there and we got the negative of h of t out, then it'd be an odd function. If we got some oddball mixture of positive and negative signs, it's neither even nor odd. But there's how you check for even and oddness. It needn't always be even powers of exponents. Absolute values let us determine an even function. Cosine function is an even function. Sine function is an odd function. If I've remembered it correctly. They have more of this later, but they have those kinds of symmetries we were talking about. And I don't see anything in sight with even powers of x when I talk about trig functions. We might someday. Not in Calculus 1. Back to the notes. Okay, I somewhat object to this terminology. I'm going to read it to you because it's in the book. A linear function is a function of the form f of x equals mx plus b. where m and b are constants. You know, when you graph these, you get a line of slope b and slope m and y-intercept b. Here's some examples of some graphs of linear functions where b is taken to be 0. And the slope, the m parameter is the slope. When m is big and positive, we get these lines that are steep and going uphill in red from left to right. When m is negative in yellow, the lines are going downhill. They've graphed lines with slope -1 and -3. And the bigger in magnitude that negative number is, the steeper downhill they go. Slope -1, downhill at this rate. Slope -3, downhill at this rate. Slope -5, steeper still and downhill. Positive slope, slope 1, going uphill. Slope 2, steeper. Slope 3, steeper still. Slope 1/2, less steep. Slope 0, be a horizontal line, by the way. So these are called linear functions. A little word of warning here. You may well have linear algebra in your future, and they'll talk about things that are linear there, and it won't be like this. It'll be something somewhat different from what this book's calling linear. They're calling a function that when I graph it and get a line, they're calling that a linear function. Yeah, all right, this is offer only valid in this class. The term linear function or linear transformation is going to be a little bit different, maybe in some other settings. There's a whole class we have on linear algebra, and the linear there doesn't mean this kind of thing. It means something else. So I'll just leave it at that. In here, we'll talk about graphing lines a little bit. A power function is a function of the form f of x equals x to the a power, where a is some constant. Okay, so we'll start covering some ground now. The book's just going to give us a bunch of examples of power functions. If we graph x to the 1 power, of course, we just get a line with slope 1. We graph x to the 2 power, y equals x squared, we get a parabola. We graph y equals x cubed, you're probably familiar with this. We get a graph of a cubic function. Y equals x to the 4th looks something like this. It's kind of like the x squared, only the shape's a little bit steeper on the ends and flatter near 0. X to the 5th, it's kind of like x cubed, but same thing. It's steeper on the sides and flatter around 0. Let's see, this is symmetric with respect to the y-axis. It's an even function. This is symmetric with respect to the y-axis. It's an even function. These other three, this one, x cubed and x to the 5th, are symmetric with respect to the origin. They're odd functions. Some observations about power functions. Domain is all real numbers. No asymptotes. This one's a parabola. This one's a line. The others don't really have geometric names like that. You only get a parabola when dealing with squaring, even though we may have some other things that look like parabolas. The right-hand part of this looks like a parabola, but it's not. It's a different shape, very subtly different. It's not the same shape as what we have over here. So the only time we get parabolas is when dealing with squares. If we were to take negative exponents, say -1 and -2, and we graphed x to the -1 or 1 over x, and x to the -2 or 1 over x squared, then we get things that look like this. All right, it's getting a little more interesting. What's the domain of these two functions? Not 0, can't divide by 0. So the domain is, scanned it from the book, the domain is all real numbers except for 0. What could go wrong? Division by 0, maybe square roots of negatives, but there's no square roots, so not an issue. So the domain is everything except x equals 0. We can find the range because we've been given the graph. But maybe some other interesting stuff is, hey, it's got a vertical asymptote of x equals 0. So does this one. And their behavior is somewhat different at those vertical asymptotes, but in both cases we have a vertical asymptote of x equals 0. The y-axis is a vertical asymptote. And this one has a horizontal asymptote of y equals 0, and so does this one. And they behave somewhat differently, but in both cases, y equals 0 is a horizontal asymptote. So when we look at these power functions, they have asymptotes. There was none of that stuff in the first collection of them. And here's some more power functions. The square root function. This is half of a parabola. It's related to squaring. This actually is a parabola. Cube root function looks like this. It's not, that's not parabola. This thing here looks like a parabola, sort of, but it's not either. You only get the parabolas when you have squaring functions. Y equals x to the 3/2. That 1/2 means there's some square root stuff involved in this. So that's kind of the reason it stops there. It's not defined for negative numbers because of square roots of negatives problems. Y equals x to the 2/3. I don't want to get into these in depth just yet. We will in chapter 4. This one's a little bit different. It's got a little sharp point in it there at 0. That's the kind of thing we'll be talking about when we address derivatives. These existence of these sharp points might be called a corner or a cusp of the graph of the function. More of that in chapter 4. But there's some examples of some graphs of power functions for some fractional values of A. A very common type of function is a polynomial function. Polynomial functions are of the form a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, down through a multiple of x squared, a multiple of x, and a constant term. The degree of this polynomial is this natural number n, whatever the highest power of x is, being a natural number power and a non-negative integer power. And these numbers in front, these things are called the coefficients of the polynomial. Polynomial functions are, these are combinations of some of the power functions. We got some graphs. Yeah, here's some graphs of polynomials. Here's where I can belittle your graphing ability. Maybe not so great at graphing polynomials. You might have some tricks from pre-calculus, some useful approaches, I should say, from pre-calculus. But still, you're a little wobbly on graphing polynomials. Yeah, it's because you ain't had calculus. In calculus, we'll have a good approach to go through and see what graphs of polynomials look like. So here's 3 graphs of various polynomials, no particular collection of 3. Things to notice are, hey, sometimes these increase. They're increasing here, it's decreasing there, and it's going uphill again, it's increasing again. They're smooth. They don't have any of those corners or cusps like we encountered previously. Their domain is all real numbers. Polynomials are defined everywhere. They wiggle. I'm trying to foreshadow a concept from chapter 4. It goes up and then it kind of wiggles around and turns back down, and then it wiggles again and goes back up. This one wiggles a little bit more. It's a higher degree polynomial. The higher the degree, the more wiggling up and down I expect to see. Where do they wiggle? No clue. That's a calculus question. Where these things change from decreasing to increasing, where they turn around, you don't have a way of finding those points until you've done some calculus. Once you have that in hand and you know where these functions are increasing and decreasing, you'll be pretty good at graphing. You'll be able to graph polynomials as good as anybody else after calculus 1, after chapter 4. This one's higher degree still. It doesn't seem to wiggle. Well, it doesn't wiggle any more than this one does. This one wiggles, turns around 3 times. This one turns around once, twice, and a 3rd time it looks like. Yet this is a degree 8 polynomial. Must have something to do with these factors. Anyhow, polynomials look like that. You wouldn't be expected to graph them yet, but you will once you learn some calculus stuff. Rational functions, I know this is kind of drinking from the fire hose here. There's a blast of definitions, but we're reviewing an entire academic year of pre-calculus in a few sections, so it's going to go fast. A rational function is a quotient or a ratio. Right? It's a ratio. That's why they're called rational functions. It's a ratio of polynomials. So a rational function f of x would be of the form p of x over q of x, where p and q are polynomials, the kind of thing we just defined. Some graphs of rational functions are as follows. Let's see, some notice about what we're about to see. The graphs are sometimes increasing, sometimes decreasing. The graphs are smooth, no sharp corners. They can have horizontal asymptotes, vertical asymptotes, or oblique asymptotes. The domain is all real numbers where the denominator is non-zero. All right, so here's some graphs of rational functions. And yeah, they're smooth, no corners. It's decreases and increases and decreases. This one looks like it has a horizontal asymptote. A little red line indicates a horizontal asymptote. This one's got a vertical asymptote. What is this one? 11x plus 2 over 2x cubed minus 1. We get division by 0 somewhere. It's 1 over the cube root of 2, so we get division by 0. It's hard to put my fingers on the precise value, but there's some place where this derivative is 0. Where this denominator is 0. That's where that vertical asymptote is occurring. This one's got a vertical asymptote. Oh, this one's easier. The denominator is 0 at what? Negative 4 over 7, negative 4/7. So that one has a vertical asymptote there. And they've drawn another red line here. This one actually has an oblique asymptote, sometimes called slant asymptote. It's an asymptote that's neither horizontal nor vertical. We will deal with this in great depth soon, chapter 2. Yeah, I think chapter 2, about exactly what an asymptote is, in particular a horizontal asymptote. It's not something the function gets closer and closer to, but never gets there. Now look at this one. This one has a horizontal asymptote given by this red line, yet it gets there. It crosses that asymptote right there. Now over here on the side, it looks like it is getting closer and closer. It probably never gets there. But that's not what a horizontal asymptote is. It's a more complicated thing than that. Details to follow when we deal with limits in chapter 2. Okay, so that takes care of a lot of algebraic stuff. There's more functions than just polynomials and rational functions, but the class of functions that deal with polynomials and algebraic operations of adding polynomials, subtracting polynomials, multiplying polynomials, dividing polynomials, taking roots and combinations of these. These are called algebraic functions. So algebraic things are multiplication, powers, natural number powers, maybe integer powers of x, square roots, cube roots, division. These are algebraic manipulations. And these combine, I know this is very vague. I can give you a precise definition, but you don't want it. It's usually covered in, oddly enough, in a senior level class. But what's not algebraic is stuff like trig functions and logarithms and exponential functions. So when I say algebraic, I mean some combination of multiplying, dividing, adding, subtracting, raising to integer powers or maybe fractional powers, which includes the extraction of roots. What's not algebraic, if a function is not of that type, it's called a transcendental function. And as far as we're concerned, the transcendental functions are logarithms, exponentials, and trig functions. So what we'll be considering is the huge class of algebraic functions and the really kind of small class of transcendental functions of logs, exponentials, and trig functions. Well, we'll kind of combine the two as well, creating more exotic transcendental functions. But the title of the book we're using is called Early Transcendentals. What that means is we're into the logs, exponentials, and trig functions pretty early on. Let's save trig functions and a little bit of the logs and exponentials for later. But for now, they insert the definition of an exponential function because they're going to graph them, and a log function. A function of the form f of x equals a to the x, where a is positive but not 1, is an exponential function. The inverse function of an exponential function is a log function. So we get y equals log base a of x if and only if a to the y equals x. Inverse functions, more of that, and I think it's in section 1.5 in the preliminary chapter that we're talking about now. We could look at graphs of some exponential functions and some log functions, and this should look familiar whether you remember the subtle details. That's why we're reviewing it. If we were to graph the y equals 2 to the x function, we get this blue function. And what's going to happen is it's going to start growing like crazy. It's going to grow exponentially fast. The red function, y equals 3 to the x, similar shape, starts to grow a little bit faster, turns out. And the 10 to the x function grows exponentially fast. There's an intimate relationship between all of these exponential functions. In some sense, they're all scaled versions of the same function. I think I want to put this on the back burner for now. What we've got here is exponential functions where the base is between 0 and 1. They've written them differently. They're mirror images of what we have over here with respect to the y-axis, so they kind of flip them around. Let's put that on the back burner, and let's look at log functions. Log functions look like this. They've graphed 4 of them. Log base 2. Log base 2 in blue would be the inverse function of the 2 to the x function. Log base 10, common log in yellow, would be the inverse of the the inverse of the y equals 10 to the x function over here. That's the correspondence between the function and its inverse. Whereas exponential functions grow like crazy. When x gets big, the exponential function gets huge. 10 to the x, we hit 1, takes on the value 10 to the 1. It must be this point right here. By the time we get to 2, it's up to 100. By the time we get to 3, it's up to 1,000. By the time we get to 6, it's up to 1,000,000. So it's growing really crazy fast, exponentially fast. Whereas these functions grow quickly, log functions grow agonizingly slowly. So a log function, it doesn't have a horizontal asymptote. It continues to move upward. You move to the right, that function increases. You move a long way to the right, it doesn't increase by much. That's the reason logarithms are used to describe ranges of really large things. Logarithmic scales are used to define decibels, for example, in sound. So the falling of a feather on a desktop makes a very soft sound, but it has a decibel reading. So does the launching of the space shuttle. And they can put both of these two events on the same scale. It's a logarithmic scale. And then that scale only ranges over a matter of 100 odd decibels without having it range over billions and billions, making it an unwieldy scale. Richter scale for earthquakes is a logarithmic scale. Stellar magnitudes, the brightness of a star in the sky, is measured on a log scale. The dimmest star you can see with your naked eye in a really dark sky is about magnitude 6. The sun, can't miss it, is about magnitude negative 20 something, negative 24, I think. So they're ranging from the brightest thing in the sky to the dimmest thing in the sky you can see with your naked eye. Over a scale, it's only about 30 units. The brightness, the energy that's output is way different, but that's the use of a logarithmic scale. It squishes down a huge range of x values to a small range of y values. Exponential functions over here, they take a little bitty bit of x values and stretch them over a tremendous range of y values. Yeah, there's a interplay between how the x's and y's act over here versus how they act over there with the logs. That's because they're inverse functions of each other. Okay, a couple more examples and that will do for this section. Okay, a little applied problem. It says the figure shows a rectangle inscribed in an isosceles right triangle whose hypotenuse is 2 inches long. Okay, so this is the hypotenuse. It ranges from -1 to 1 along the x-axis. That's 2 units. It's isosceles. Okay, it's isosceles right triangle. Here's the rectangle that they seem to take an interest in. They say express the y-coordinate of point P in terms of x, and express the area of the rectangle in terms of x. So here's the x value. Imagine that sliding back and forth. As x moves, this point that has as its first coordinate that x value, this point's going to slide along this line. We want to figure out what the y-coordinate of the point is. All we need is a relationship between x and y along this line. And then we'll be able to express y as a function of x. And it's a, as the book says, it's a linear function because its graph is a line. Oh, and once we have x and y, we'll know the dimensions of this rectangle and we can find its area. So that's the plan. First off, let O represent the origin of the letter O versus the number O. They've used the 0 number along the x-axis is what they have here. I know the fonts look a lot alike, but I want to talk about triangle AOB. AOB is also an isosceles triangle. It's similar to the big triangle, the given isosceles triangle, angle, angle, angle. They're 45, 45, 90 triangles, both of them. So anyhow, this right-hand triangle, AOB, is an isosceles triangle. So the length of this side is the same as the length of that side. Isosceles triangles have two sides of the same length. So this side has length 1, so this side must have length 1. And point B must be 1 unit above the origin, so the coordinates of point B must be 0, 1. All right, so we got 2 points on this line, the point 1, 0, point A, and the point 0, 1, point B. So let's find the equation of the line that passes through point A and point B. That is through point 1, 0 and point 0, 1. Slope, let's label these x1, y1, x2, y2 for A and B respectively. And the slope is change in y over change in x, y2 minus y1 over x2 minus x1. The way we've labeled the points, y2 is 1, so we have 1 minus y1, y1 is 0, 1 minus 0, x2 minus x1, x2, that'd be 0 minus 1, 0 minus 1, simplifies to negative 1, so the slope's negative 1. Oh, duh, slope's negative 1, rise negative 1, run 1, if you like. So anyhow, there it is. Algebraically, you want to do it geometrically, fine. So there's a slope. We need a formula for the line. Let's use the point slope formula because we've got a slope, it's negative 1, and we got a point. Actually, we got 2 points. Use either one of them. Say y minus y1 equals mx minus x1. So I'll use this point. Doesn't matter. You want to use the other point, you'll get the same thing, the same line. Y1 is 0, 0. X1 is 1. We get a 1 there, and the slope was negative 1, so we get y minus 0 equals slope x minus 1. Simplifying, we get y equals negative x plus 1. That's the equation of this line. So this point P, having x coordinate, variable x, the y coordinate will be given by this. So point P is of the form x comma negative x plus 1. And the y coordinate of P in terms of x is negative x plus 1. They asked the question like that, so that's the reason I'm wording my solution like that. Also, trying to be conscientious when the answer is just a single little equation or number, try to put a square box around it so I can call attention to and the fact that I've answered the question they asked. So that gives us the coordinates of point P. It's x, negative x plus 1. The next thing they wanted to know was what's the area of this rectangle in terms of x? Okay, how wide is the rectangle and how tall is the rectangle? X is the distance from the origin to here. Actually, the rectangle's twice that wide. So the width of the rectangle is 2x, and the height would be the y value. Width is 2x, height is y, area is width times height, would be 2xy. But we know from part A that y is negative x plus 1. That's the equation for this line. This point is on that line, so that's the y coordinate in terms of x. Substitute that in, and there's the area as a function of x alone. You want to multiply it out and go right ahead. We don't have to do anything to it, so I may as well leave it like that. Maybe passing comment. This only makes sense when x is between 0 and 1. I mean, I can take this point, slide it around, and get all sorts of things I want. Yeah, I won't have a positive width and positive height unless I take x between 0 and 1. So area becomes a meaningless concept when x is outside of this range. You might even argue with having an area of 0 is meaningless. I'd try to talk you out of that. Area of 0 is okay. Negative areas are no good, though. A distance of 0 is okay, but not negative distances. But there's area as a function of x as they want. Okay, many of the applications in calculus will start out with problems of this sort. A calculus question would be, okay, you see this rectangle here? How big can you make the area of the rectangle? You can't answer that without calculus. Maybe. Think about it. If we make the rectangle really wide, it can't be very tall because of being stuck underneath these, or stuck inside this isosceles triangle. If it's really wide, it won't be very tall and it won't have a very large area. We'll make it really tall. If I make it really tall, then it's not going to be very wide because it's stuck inside this isosceles triangle. So what would you choose x to be to maximize the area? That's the kind of questions we'll look at in calculus. So that'll be some of the applications of derivatives to max-min problems, extrema problems in chapter 4. So that's the reason they're asking these kinds in these preliminary chapters. Here's another one. Not really that complicated. These are the kinds of questions they would ask in terms of an extrema question or a max-min question. Here they're talking about how much something costs. The calculus question would be, how do you minimize cost? It would be an extremum value question. And here's a story and a little picture. A power plant sits next to a river where the river's 800 feet wide. Here's the power plant, 800 feet across the river. To lay new cable from the plant to a location in the city 2 miles downstream on the opposite side costs $180 per foot across the river and $100 per foot along the land. So what they're going to do is they're going to run a cable in the water and on the land. They want us to calculate, given these costs per foot, how much it would cost as a function of x. Well, we could go straight across the river and straight over. That minimizes the amount of cable used in the river. Yeah, but it makes this other one pretty big. We could run a straight line distance. We could run straight across. That would minimize the amount on land. Yeah, it's probably not going to give you the cheapest option though. But anyhow, what they're telling us in part A is, suppose the cable goes from the plant to a point Q on the opposite side that is x feet from point P directly opposite the plant. Here's point P directly opposite the power plant. So they've moved over a little bit. So what they're going to do is go at an angle across the river, determined by this distance x, and do the rest of it along the land. Write a function, c of x, that gives the cost of laying the cable in terms of the distance x. Okay, So as x varies, the cost will vary. I want some neat balance between minimizing, I want to minimize cost. That's beyond us at this stage. But that's the question. Part B says, generate a table of values to determine if the least expensive location for point Q is less than 2,000 feet or greater than 2,000 feet from P. Okay, so that's the X value they're talking about there. We'll do that reluctantly. I'll do that. That's not a good question. It just shows you how hard it is to find extreme values without calculus. But we'll make a little table and make a guess. All right, so we need to figure out how far that is and how far that is. It costs $180 per foot here, costs $100 per foot along the land. So we need to find those distances in terms of X. Okay, they've done this thing to you. They've mixed together feet and miles. So first off, let's take that 2 miles and write it in terms of feet. 5,280 feet in a mile. So we're looking at 10,560 feet for the 2 miles. So let's do everything in terms of feet. They gave us cost per foot. So it only makes sense to express everything, everything in terms of feet. Okay, so first off, how much cable is there on land? Well, it'd be 2 miles, 10,560 feet minus X. That's the distance from here to here, so no problem. That's the amount of the cable that lies along the land. 10,560 minus X feet. Let's see, the power plant, point P and point Q form a right triangle. Power plant PQ, right triangle. One side is 800 feet, another side is X feet, and it's the hypotenuse we're interested in. Well, 800 squared plus X squared equals hypotenuse squared, Pythagorean Theorem, or hypotenuse is the square root of the squares of these added together. So 800 squared plus X squared, square root of feet, that's the length of the hypotenuse, and that's the amount of the cable that runs on the river or under the river. So we found the amount of cable in terms of X. We know the cost. Cable costs $180 per foot across the river. So the distance is this. We'll multiply it by $180 per foot, and we'll get 180 times that distance dollars. $100 per foot on land. This was the distance on land, 10,560 minus X. So we'll multiply that by 100. Units will be dollars, and we get 100, 10,560 minus X. That's the cost on land. This is the cost across the river. Add them together, and there's the total cost. So there's the cost as a function of X. Of course, what we want to do is minimize cost and find a minimum value of this function. And that's the kind of thing we can do with calculus. They've told us, take this cost function and make a table and try to guess what's happening. They were interested in 2,000 feet. So we'll plug 2,000 feet in. I'll grab the calculator out and just crunch the numbers and round to the nearest penny. When X is 2,000, I produce this number. Let's go 100 feet back, about 3 steps and 100 feet forward. Let's go back 1,900, 1,800, 1,700 for X, and then greater by 100 and see if there's a trend, and there is. Looks like it costs more when we increase X here, and it costs less when we decrease X here. They asked the question, determine if the least expensive location for point Q is less than 2,000 feet or greater than 2,000 feet. Here's 2,000, it gets more expensive for X greater than 2,000, it gets less expensive for X less than 2,000. So my guess is less than 2,000 feet will yield a less expensive option. How much less? Well, I need either calculus or a bunch more numbers cranked out. The estimating with the numbers is a crude way to do it. There's a pretty clean way to do it using calculus. But these are good illustrations of kinds of things we'll do in the calculus material. And that takes care of section 1.1 And some of the remedial stuff we'll have to do. So it ain't a bad idea to re-expose you to some of these ideas before we jump into all the calculus stuff. But we'll go through a few more sections in chapter 1, and I will see you in those sections shortly. Have a nice day.